Hi, my name is Sky Sweeney. I'm an embedded software engineer for my day job, and with my spare time, I'm an electronic hobbyist. And for the last couple of years, I have been working on an AVC, the Sparkfun Autonomous Vehicle Competition entry. And although I haven't made it out yet, I am continuing to working on it, trying to get out there perhaps in 2014. During my system design of this, I kept coming up with the same problem, that determining of heading was one of the hardest things to decide. GPS gives you position pretty well, but heading is kind of difficult. So there are a couple of solutions out there. The first is using a gyroscope. Gyroscopes give you angular rate, and if you sample them fast enough and integrate, you should be able to get heading. The problem is most gyros that hobbyists can afford are MEMS based, and they have significant drift and significant temperature issues. They change over temperature, and in an RC car where it's vibrating around, there's so much noise in the gyro that accelerating it is very difficult. It's okay in the short term, a couple of seconds, but anything over that, the drift starts to become too large to really rely on heavily. Second solution for heading is GPS, but GPS only tells you what your heading was. It doesn't tell you what your heading currently is. And the way it does that is it knows where you were the last second when it did an update, and it knows where you are this second, and it can do the calculation to determine heading. Like I said, it only tells you what your heading was, not necessarily where you're heading currently. It's better than nothing, but it's certainly not ideal. The other sensor that's often used for heading determination is a magnetometer. 2 or 3 axis magnetometer can determine where the field is strongest where you are, and that would point towards the North Pole. They work very well in a magnetically benign environment, but in an RC car where they're sitting next to servo motors and very high current DC motors to drive the RC car, magnetometers are almost worthless. You have to move them away quite a ways from the motors. Maybe wrap the motors in something like mu metal to shield them. It gets very complicated and difficult to manage. So I kept coming back to, how was I going to determine my heading? And just recently, I noticed on the Do-It-Yourself Rovers Google website that somebody else had come up with an idea that I came up with about a year ago, and that's to use the sun. At my day job, I work with all kinds of non-magnetic heading sensors, and the 2 basic classes are those that need to remain motionless and sense the Earth rotating out from underneath them with very expensive sensors like ring laser gyros. MEMS gyros aren't up to the task in any short amount of time. So these you put down on a granite block and let them sit for a while, and then they would tell you where north is. Not very useful for an ABC competition, and way outside the ability of me to afford. The second class is a little more interesting, and that's a device that has an eyeball and it looks up into the sky and takes a photograph, and it either tries to find the big bright sun or all the little tiny stars, and it does a whole bunch of complicated math to figure out which way north is. And these work pretty well, but you do have to have visibility of the sky, cloud cover if it obscures the stars, or cloud covers even if it masks some of the sun. These sensors tend to break down and not work very well. They're also quite expensive, not nearly as expensive as the ring laser gyro systems, but still well outside the scope of the average hobbyist. But these celestial systems gave me an idea, and that was, rather than looking with a picture for the sun, why not just spin a sensor around and look for a really bright spot? and the brightest spot hopefully would be where the sun is. And that's the system that I came up with. Tentatively, I'm calling it a SUNDAR, although I'm probably going to change the name because SUNDAR appears to be an Indian name, very popular name, and if you Google on SUNDAR, you get thousands of hits that have nothing to do with my project. So I'm going to show you my system and go through the different parts and explain to you how it works. You can see a lot of my blog that I've been working on for the last couple of years on this. You can find that at www.fll-freak.com/blog, and there you can see the rantings that I've been doing over several months about the SUNDAR, and just recently some of the successes that I've had. So I'm going to pause and reposition the camera so that you can see the unit and we can go through the various parts. So here's the basic system in operation. What you can see here is the rotating sensor head. On the back side here is a light sensor, and its field of view is narrowed by this slit, and only light can enter a very small slit in the front, which we'll show you later. But it's looking out here at this what I call stupidly bright LED. It's a multi-watt Luxon LED with a heat sink on the back. It draws a little over an amp at 3.3 volts. Very bright LED, it's hard to look into. But that's my pseudo sun right now. And as you can see, the sensor head is rotating back and forth centered around where the light is. Driving the sensor head on the bottom is a little stepper motor, and that's a Pololu NEMA 8 stepper motor. It's got a 1.8 degree step angle, but the motor driver that I'm using does micro stepping, and I have it currently set for 32 micro steps per step to get the finer resolution. You can see off to the side here is a little optical brake sensor. There's a tab on the front here that I used for getting a zero position. We can go over that in a little bit. To get the sensor off of the rotating platform, the wire comes down and runs under a spool that's here, and the takeoff comes up and then down to the circuit board. I'm not using slip rings. I had started using slip rings, but the complexity of trying to do that and the noise that they added was much more difficult. So I'm just using the finest 3-wire ribbon cable that I could find, wrapped around about 5 or 6 times around the center spool before coming up. So down here is the motor driver, and it is a Pololu DRV 8824 motor driver. Very nice little unit. I very much like it. It's a step and direction type controller. It runs this bipolar motor. It runs, oh boy, I can't remember the exact specs, but like 8 to 24 or maybe even higher voltage, and about an amp per phase. And that's kind of what this beast needs in order to maintain good stepping. It needs a significant amount of current. The motor driver is being controlled by, over here, a little Arduino. This is a Sparkfun Arduino Pro Mini, and it's got an FTDI 5-volt cable running off to my PC right now. We also have a small voltage regulator to take the 12 volts that's coming in to power the motor, and it drops it down 5 volts to power most of the electronics. The last major component on here is a 3-axis gyro, and that's an Adafruit L3 GD20 3-axis gyro. I like this one a lot because it already has the voltage level converters on board, which some of the other units based on the same chip do not. Some minor components. I have a thermistor on the motor, and it comes down to a voltage divider and to one of the analog inputs on the Arduino to make sure that I don't burn up the motor. The motor is actually spec'd to go up to close to 200 degrees Fahrenheit, but I currently have it shut down around 200. And I have a little status LED here, which will blink or go on solid during some phases of operation, and will blink in the case of errors. And over here on the scope, you can see these traces, those little blips. That's the output of the light sensor currently. You can see that when it's not looking at the sun, it's a low voltage, and each time the sensor sweeps through the bright LED, you can get a significant spike that's quite easy to detect in the Arduino. So the way this works is if I reset or start up power, first thing that's going to happen is the sensor is going to wind up as much as it possibly can, and you'll see it stutter. That's because when the coil of wire reaches its maximum, it can't go anymore. The step driver kind of freaks out, a stepper motor, and it zips back, and then it goes forward, zips back. But at some point it gives up, and then it goes back until the tab here, seen by the optocoupler, it then unwinds one more time, calls that the 0 position, and then it does a full sweep looking for the sun. Once it finds the sun, it goes back and it starts to hunt on it. So I'm going to go ahead and reset the processor, and we'll watch it go through its initialization. The first thing, the bright light LED comes on. That's us taking out the gyro cal, the bias offset. There's the stutter I was talking about. It's coming back, finding the 0, unwinding once more, and then doing a quick scan, finding the sun, finds the sun, starts scanning. The LED coming on solid indicates that we're sampling the gyroscope when there's no activity, trying to figure out what the analog, or I'm sorry, not the analog, but the digital output of the gyro is in a motionless condition. And it's sitting there waiting for that to stabilize to a constant value. Once that's stabilized, it continues. If you were to shake the base during that period of time, you wouldn't find a stable value, and it wouldn't go. It wouldn't go on to the next step. It would wait until the base became motionless. So why the gyro at all? Well, the gyro is in here to help track. Now, if I move the light, it will indeed follow the light. You can see it moving, and it's following the light, but I'm moving that fairly slowly, and I can move it back. Uh-oh. Broke the connection. Oh, it just reacquired. It'll follow the light, but that's not the normal case. The sun isn't going to be moving. It's the base platform that's going to be moving. And if I shake this or spin this very quickly as if the RC car was making a 90-degree turn, it might spin so fast that this would come out of the field of view. So the gyro tells the Arduino, hey, your base has moved 35 degrees to the right. You better look for the sun that direction. And indeed, let me just disconnect the oscilloscope here for a second. If I were to shake the base or spin the base violently, we'll see that indeed it continues to track the sun without losing lock. If I didn't have the gyro to provide that feedback, it would not be able to do this. It would come out of the field of view very quickly, and it would lose lock. But here I can spin it, whoops, I can spin it around quite a bit without losing lock. So right now I have the light sensor is facing, it's horizontal. My later designs, this is on a gimbal. Let's see if I can lift it up gently. It's on a gimbal that would come up. Whoops, I lost the sun there, but it reacquires. It would come up to meet the sun at whatever elevation it is. I am working currently on a design for a head that I have some friends at work who have access to a 3D printer, and they will print me this device with a very, very narrow slit on the front. The light sensor will snap into the back, very fine screws in order to adjust the elevation, and an entire dome over all of this, so that as the car is running through the air, this doesn't act as a sail and knock the, because you know, if the wind were to push this, it could push it off kilter and get it all screwed up. So a little dome over the entire thing to get rid of the blast. So that's the current operation. I'm going to reset it because I've lost the 0 right now. I'm going to reset it. And I'm going to go back. It's going to wind up. And it can't wind up anymore. And it's then going to find 0. It's going to back up. Another full turn. Scan. Look for the sun. Find it. And 0 in on it. Now what we're going to do is quickly move over and show you the CRT screen and see what the output might be to the rest of the system. So we're going to reset the camera now. So now what we're looking at is the output of the Arduino's terminal screen. My software is currently printing out notices of events. The first number you see there, the one that's like 79 or 80,000, whatever, that very large number is the number of milliseconds since the power, actually I think it's microseconds, yeah, number of microseconds since the power was applied to the system. NTC indicates that this is a notice. There are DBGs for debug and ERRs for errors. Currently we're not experiencing any of those, and I have the debug ones turned off because I'm pretty much out of development now. The following two numbers, the first one, the 3,760, 70, whatever, that is the number of microsteps where it found the sun. Now it just so happens that this is a 200 step per turn motor, but I am using 32 microsteps, which means that 6,400 steps per revolution, which just happens to be the same as an artillery mill. It's a unit used by the military for Azimuth, an artillery mill. So 3,700 artillery mills is where it continues to find the sun. The next number, the 101, 104, 102 number, is a figure of merit. It is basically a quantitative measurement of how high the peak is compared to the average signal that we saw during the particular sweep. The larger the number, the higher the probability is that we've actually found the sun and not some bright light in the room. The last number is the temperature of the motor, currently at 126 degrees. Probably an understatement. I think the thermistor that I'm currently using may not be rated for the temperature extremes that this motor is going to generate. I need to go find myself a better thermistor. So this data is coming out twice a second, and that could then feed into the processor that is running the AVC robot to know what the heading is based off of this sun radar system and what the figure of merit is, so whether or not it should trust it. Now I'm going to block the LED with my hand. You won't be able to see it, but what you will see is the figure of merit goes to 0 because it hasn't a clue where it is anymore, but the gyro continues to maintain where it thinks it is. And then I take my hand out and it will reacquire. Now I do believe there's a little bug in there because it went to 3,200 instead of saying at 3,700. I do still have a few issues that I need to take care of. Last thing is, if the temperature ever goes above the 200, the system shuts itself down, turns off the motor driver to allow it to cool down, and it'll then start up in the future. So that's a basic summary of my system. I have yet to try the entire system outdoors, but I have tried the sensor. I've taken the sensor head outside, and in bright sunlight the sensor head gets completely saturated, so I will need to put a couple of neutral density filters in front of it. I found that 3 1.2 neutral density filters, which means that less than 1% of the sunlight is hitting the sensor, is what it allows it to work out of saturation. By the way, that sensor that I'm using is an Adafruit log scale light sensor. It's a GA1A12S202. Big part number for a little tiny chip. Let's see if I can find one. So there's the chip. The actual sensor is a little tiny chip in the top row of parts in the center. Very small, but I plan on using the entire breakout board minus the headers. I'm just going to solder the wires directly to it, and that will snap into the back of the sensor head. So my next stages are to remove some of the last software bugs and to get the design files for the 3D printer to make the head, and then I need to make a circuit board rather than the breadboard here. Make a circuit board, miniaturize it, mount it on an RC car, and start taking it outside to get it to work. So there you have it. I would be happy to take comments. I will start monitoring the Do-It-Yourself Rovers website, and you can certainly leave comments for me on my my blog at www.fll-freak.com/blog. Leave me a comment there. I'll be happy to answer what I can. Thank you for watching this, and if you make any progress yourselves, please let me know. Thank you.